Hello, welcome to today's class. In today's class, we will talk about decoders. A binary code of n bits is capable of representing up to 2 to the power n distinct elements of coded information. We have seen in one of our earlier class that when you have 3 bits, we can represent 2 to the power 3, that is 8 different things. And if we have, for example, 4 bits, we can represent 2 to the power 4, that is 16 different things, and so on. A decoder is a combinational circuit that converts binary information from n input lines to a maximum of 2 to the power n unique output lines. So a decoder has n input lines and a maximum of 2 to the power n outputs. If the n-bit coded information has unused combinations, the decoder may have fewer than 2 to the power n outputs. Now let us talk about the 2 to 4 decoder. As we can see from the graphical symbol of the 2 to 4 decoder, we have two inputs, W0, W1, and we have 4 outputs, Y0, Y1, Y2, Y3. Here is the truth table of the 2 to 4 decoder. When the two inputs W1, W0 is equal to 0, 0, then Y0 output is equal to 1 and the remaining 3 outputs are equal to 0. When the two inputs are 0, 1, then Y1 is equal to 1 and the remaining 3 outputs are equal to 0. When the inputs is equal to 1, 0, then Y2 is equal to 1, and when the input is 1, 1, then Y3 is equal to 1. So if we consider the input as a binary number, then the number is getting decoded to assert the corresponding output. When it is 0, 0, Y0 is getting asserted. When the input is 0, 1, the decimal equivalent of 0, 1 is 1, then Y1 is getting asserted. When the input is 1, 0, the decimal equivalent is 2 and the output Y2 is getting asserted, and so on. Now a n-bit code in which exactly one of the bits is set to 1 at a time is referred to as one-hot encoded. Now if we want to build the logic circuit from this truth table, we have to find out the Boolean expression for each of the 4 outputs, Y0, Y1, Y2, Y3. And from our previous class, we know that we can represent, one way to represent the outputs is using the sum of minterm expression. For example, if we want to find out the Boolean expression for Y0, we see that Y0 is equal to 1 only for one input combination, and hence the sum of minterm expression for Y0 will have only one minterm, and that minterm is W1 prime, W0 prime. Similarly, for output Y1, Y1 is equal to 1 for only one input combination, and hence the Boolean expression for Y1 will be W1 prime, W0. In the same way, the Boolean expression for y2 will be w1 w0 prime, and for y3 the Boolean expression will be w1 w0. Now with these Boolean expressions decided for each of the four output, we can now build the logic circuit, and here is the logic circuit for the corresponding Boolean expressions. And as you can see, we are calculating y0 as the end of w0 prime and w1 prime, and we are calculating y1 as the end of w0 and w1 prime. So this is the logic circuit for the 2 to 4 decoder. Now we can add enable input to the 2 to 4 decoder, and it will be the 2 to 4 decoder with enable input. What's the meaning of the enable input is that if the enable input is 0, then all the outputs will be equal to 0. What we saw in the previous truth table is that at any point of time, depending on what the input is, one of the outputs are equal to 1. It's never the case that all the outputs are equal to 0. But now with this enable input introduced, when the enable input is equal to 0, all the outputs will be equal to 0. And when the enable input is equal to 1, the logic circuit will behave like the 2 to 4 decoder we saw in the previous slide. So here is the truth table for the 2 to 4 decoder with enable input, and as you can see, when the enable input is 0, it doesn't matter what the value of w1 and w0 is. It may be 0 0, it may be 0 1, it may be 1 0, it may be 1 1, it doesn't matter. As soon as the enable input is 0, all the outputs will be equal to 0. And when the enable input is 1, the outputs are same as we saw in the previous slide. With enable input 1, if the w1 w0 inputs is 0 0, then y0 will be equal to 1. If the inputs w1 w0 input are equal to 0 1, then y1 will be equal to 1, and so on. Now to build the logic circuit, we first have to come up with the Boolean expression and for each of the output, and we can see that the Boolean expression for y0 will be equal to en w1 prime w0 prime. Y1 will be equal to en w1 prime w0, and so on. And based on this Boolean expression, we can build the logic circuit as shown here. This logic circuit is same as the logic circuit we saw in the previous slide, with the only difference that the enable input is also connected to all the AND gates. Now here is the truth table for the 3 to 8 decoder. So 3 to 8 decoder, we will have 3 inputs, we will have 8 outputs, and again, if we consider the input to be a binary number, it is being decoded to assert the corresponding output line. For example, when the input is 0 0 0, D0 is 1. When the input is 101, that's decimal 5, then D5 is equal to 1. And when the inputs is equal to 111, which is decimal equivalent is 7, then D7 is equal to 1. And from this truth table we can find out the Boolean expression for each output, and then we can build the logic circuit. And as you can see, D0 is y prime, x prime, y prime, z prime. D7 is x, y, z. Now let us talk about a decoder tree, and for that let us use the truth table of the 3 to 8 decoder with enable input. So we have added the enable input to the 3 to 8 decoder, and whenever the enable input is 0, it doesn't matter what is the value of W2, W1 and W0, all the outputs will be equal to 0. If the enable input is 1, then the behavior will be same as the 3 to 8 decoder. Now we can build the 3 to 8 decoder using 2 to 4 decoders. So we are trying to build the 3 to 8 decoder, and we are making use of 2 to 4 decoders. So this is one 2 to 4 decoder, and this is the second 2 to 4 decoders. And we have since we are trying to construct a 3 to 8 decoder with enable input, we should have 3 inputs and another enable input, and we should have 8 outputs. So here is the enable input, and here are the 3 inputs W2, W1, W0, and here are the 8 outputs Y0 to Y7. Now we are connecting the inputs in such a way that the behavior of this logic circuit will be that of a 3 to 8 decoder with enable input, which means this logic circuit that we have here will implement this truth table. Let us try to understand how this logic circuit is implementing this truth table. For that, let us discuss this last row of the truth table where the enable input is equal to 0. Now in this logic circuit, whenever the enable input is equal to 0, it doesn't matter what is the value of W2, the output of the two AND gates will be equal to 0. That's because whenever one of the input of the AND gate is equal to 0, the output will be 0. It doesn't matter what the value of the other input is, because 0 and 0 is also 0, 0 and 1 is also 0. So whenever one of the input to the AND gate becomes 0, the output of the AND gate will definitely be 0, and it doesn't matter what is the value of the second input. So now since the enable input is 0, the output of the first AND gate is 0, the output of the second AND gate is 0, and as you can see, the output from the first AND gate is connected to the enable input of the first 2 to 4 decoder, and the output of the second AND gate is connected to the enable input of the second 2 to 4 decoder. Now since the enable input of the first 2 to 4 decoder is 0, if you remember the truth table, all the outputs will be equal to 0. And similarly for the second 2 to 4 decoder, since the enable input is 0, all the outputs will be equal to 0. So now if you compare the outputs here with what we have in the truth table, and they are matching. So this logic circuit, if we give the input enable input equal to 0, the outputs will be as shown in the truth table. Next, if we look at the first 4 rows of the truth table, for these 4 rows, we see that enable input is always 1 and the WT input is always 0. Now when this is the case, the output of this AND gate will be 0 because this 0 is connected to the AND gate. However, the second and since this output of this AND gate is connected to the enable input of the 2 to 4 decoder, all the outputs of this 2 to 4 decoder will be 0. All the outputs will be 0. However, for the first AND gate, the output will be 1 because both the inputs are equal to 1. This enable input is 1, so this input is 1. W2 is 0 and it goes through the inverter, so it also becomes 1. So both the inputs to the AND gate is 1 and hence the output of the AND gate is 1, which means our first 2 to 4 decoder is now enabled. And when the enable input is equal to 1, the output that we see from the 2 to 4 decoder will depend on what are the input values. So here the two inputs are W0 and W1. So now if we consider this third row, in the third row W1 is equal to 1, W0 is equal to 0. So W0 is 0 and W1 is 1. So as far as this 2 to 4 decoder is concerned, its enable input is 1 and at the input we have 1 0. W1 is 1, W0 is 0. So the input is 1 0 and 1 0 decimal equivalent is 2 and hence Y2 will be equal to 1. Y2 of this 2 to 4 decoder will be 1 and that makes the 8 outputs to be equal to 0 0 1 0 0 0 0 0 and that's matching the output we have in the truth table 0 0 1 0 0 0 0 0. Similarly, these 4 rows enable is equal to 1 and W2 is equal to 1, and when that happens the output of this AND gate will be 0 because this W2 input, when it goes through the inverter, will become equal to 0, and whenever one of the input to the AND gate is 0, the output of the AND gate is destined to be 0. But for the other AND gate, W2 is equal to 1, so this input will be 1, enable is 1, so this input will also be equal to 1, and since both the inputs to the AND gate is equal to 1, the output will be equal to 1. Since the output of the first AND gate is equal to 0, it means the enable input of the first 2 to 4 decoder will be 0, and hence all the 4 outputs of the first 2 to 4 decoder will be equal to 0. However, since the output of the second AND gate is 1, and enable input of the second 2 to 4 decoder is 1, and hence the output of the second 2 to 4 decoder will depend on what the inputs, what is the input W1 and W0, and these two inputs W1 W0 is connected to the input W1 W0 of the 3 to 8 decoder. And now if we consider this row as an example, in this row W1 is 0, W0 is 0, so these two inputs are equal to 0, and since they are connected to the W0 W1 input of the 2 to 4 decoder, for the 2 to 4 decoder its input will be 0 0, and 0 0 decimal equivalent is 0, and hence the Y0 output of this 2 to 4 decoder will be equal to 1, and this Y0 output corresponds to the Y4 output of the 3 to 8 decoder. So the Y4 output of the 3 to 8 decoder will be equal to 1, and hence the 8 outputs now is 0 0 0 0 1 0 0 0, and that's what we have in this truth table, 0 0 0 0 1 0 0 0. So output is matching that we have in the truth table. Like this you can try out all the other rows, and you will find out that this logic circuit in fact implements this truth table, and hence this is the logic circuit of a 3 to 8 decoder with enable input. And how did we build this logic circuit? We build this logic circuit by using two 2 to 4 decoders. Building decoders this way is called decoder tree. So that's all I have in today's class. I would like to ask you to build the truth table, build a logic circuit of 4 to 16 decoder, and also try to build the same 4 to 16 decoder using 3 to 8 decoders, and also by using 2 to 4 decoders. So please try out to construct the logic circuit for the 4 to 16 decoder, first using 3 to 8 decoders, and then next using only 2 to 4 decoders. Next we will see how to implement these logic circuits in Logisim. Hello. Yes. So we are now looking at how to implement the 2 to 4 decoder that we discussed in the theory class using Logisim. So as you can see, here is the logic circuit for the 2 to 4 decoder, where the Y0 output is equal to En W1 prime W0 prime. The Y1 output is equal to En dot W1 prime W0. The Y2 output is equal to En dot W1 W0 prime, and Y3 output is equal to En W1 W2. And if we try to change the values here at the output input values, we will see that we get the correct output values. For example, when the enable input is 0, all the outputs are 0. When I make enable input equal to 1, it will start behaving like the 2 to 4 decoder, and with the enable input 1 and the W1 W0 input 0 0, the Y0 output is equal to 1. If I change the W0 input to 1, then Y1 input output will be equal to 1. If I change the input to 1 0, 1 0 is decimal 2, then Y2 will be equal to 1, and 1 1 is decimal 3, so Y3 will be equal to 1. Now using this 2 to 4 decoder as the building block, we can build our 3 to 8 decoder. We are doing this in the same way that we had discussed for full adder and parallel adder. So we can use a already built block to build more complicated circuits. So here we are using the 2 to 4 decoders. So this is a 2 to 4 decoder. This is the second 2 to 4 decoder, and we are using the 2 to 4 decoder that we had built to build a 3 to 8 decoder. And the connections are made as we had discussed in the theory class. Now let's look at its behavior. As you can see, when the enable input is 0, all the outputs are equal to 0. But when I make the enable input equal to 1, now the output will depend on what these three inputs are. When it is 0, 0, 0, y0 is equal to 1. When it is 0, 0, 1, y1 is equal to 1. When it is 0, 1, 0, y2 is equal to 1. When it is 0, 1, 1, y3 is equal to 1. And when the inputs are 1, 0, 0, then y4 is equal to 1. 1, 0, 1, y5 is equal to 1. 1, 1, 0, y6 equal to 1. And 1, 1, 1, y7 is equal to 1. So this is all that I have for today's class. Before we end the class, I would like to ask you to also build the 3 to 8 decoder in this way that we have built 2 to 4 decoder, and then I'd like you to build 4 to 16 decoder using decoder trees, where first you will use only 3 to 8 decoders to build the 4 to 16 decoders, and then you will use only 2 to 4 decoders to build the 4 to 16 decoders. Okay, so we'll end our class today. Bye.